Yeah, so this morning we have Tom Cronin visiting us from the United States Geological Survey in Reston, Virginia. This afternoon he's going to be giving the annual Bolin Center Climate Lecture. And we thought we would get him just to talk a little bit more today and give us more of an informal seminar this morning where he's going to discuss some issues with sea level change. So Tom graduated with a PhD in geology from Harvard University in 1977. And since then, he's been very active in a number of different research themes, mainly associated with coastal ecosystems, some deep sea biodiversity of calcareous microfossils. And he's also done a lot of paleoclimate work. And my involvement with Tom has been limited to the Arctic Ocean, where I know he's been actively researching since the early 1990s. But he's also worked in a number of other ocean basins around the world. And he's written over 200 papers in his career and 2 really great books, Tom. And with that, I'm going to turn it over to Tom now, and he will give this morning's seminar.
Thank you, Matt, and thanks to Nina and Martin Warren here for inviting me. This is an honor and a pleasure. And as I understand it, I know you are the students and faculty who are doing this kind of research as well. So I thought the topic of sea level was good to revisit from a broad geological perspective, because most of us focus on our particular specialty in sea level, whether it be geophysics, oceanography, or quaternary science. And there's a lot going on, and so I put together a talk. It may be a little too long, but I'm going to try to go through it, and forgive me if some of it you already know well or actually doing research on it. And so I acknowledge my collaborators here, both Swedish and American, who've worked with us on it. This is not a talk on the Suarez cruise in 2014, except towards the end where I'll mention some of the things we discovered there. So sea level is obviously a hot topic in terms of the climate issues that surround it, and probably a poorly understood topic to many, but it's not easy. That's supposed to be funny, by the way. You understand why? Because, see, the farmer just went out and painted it on his silo, and that actually is sea level, because this is out in California, where you're in a valley that's below sea level. But too often we hear about sea level being discussed by scientists as well as the media and the public as being something that's straightforward. The ice is melting and sea level. Of course, sea level is falling here, so it's less of an issue. And of course, you know the reasons why, because of the methane and the CO2, most important, during the last 800,000 years, from Antarctic ice cores, and that were off the charts, over 400 now. This slide's a little old. This was during the Copenhagen diagnosis that came out about 5 years ago. And these orbital cycles, Milankovitch cycles, I'll discuss as we go on. Here's Antarctic temperature from deuterium. And later I'll show you this record in terms of sea level as derived from the deep sea oxygen isotope record, which is one of the most commonly used methods to understand sea level. We all know that we have tide gauges, and we all know that since the 90s we have satellite records that are better, but very different. They're not coastal sites, they're the global ocean. And we all know that this was the 2001 IPCC projection, Intergovernmental Panel on Climate Change. And in this particular example, the satellites were at the higher, actually measured sea level, and were at the higher end of the range projected in 2001. One of the reasons for that is, you probably know, is that the IPCC reports take the 2007 one, for example, didn't really factor in ice, believe it or not. Was thermal expansion. So we underestimated the rate of sea level rise. I don't have to tell you, the models, different models, climate models, underestimated the rate of sea ice decline too. And they underestimated the rate of ocean acidification. I'm not bashing models, there are probably modelers here. But things have changed in ways that were not predicted if we do a little historical analysis. In terms of the future, I won't get into this in detail. Pat Pepper at Instar, Colorado, put this together a couple of years ago. And these are all the different IPCC sea level rise ideas. But what matters is here's your tide gauge record in red and your satellite record, and here's the future. Okay, so what do we hear about the future? There's all kinds of ways represented by these different studies to project future sea level rise dynamically, empirically, statistically, and glaciologically, and you can take your pick, but they all come up with A, a large error bar, and B, a meter by 2100. People are very concerned about what the estimates show here. I don't think any of them are right, but people need this information, and the more we understand past sea level, which is what I've worked on, the better we're going to understand this, because the ice is, I think, the joker in the deck, meaning land ice, and changes in mass in the world's oceans. But this is just a little background on historical sea level and future sea level, and I'm sure there are papers since these were done, but I don't know if they get any better or not. So it's worth looking, and this is the latest IPCC one. Here, this is sea level in terms of meters. There's your 1 meter, and that's going out several centuries. And you can look at the contribution to sea level from different sources and get ideas on what's the total is in red here. I personally think Antarctica and Greenland margins are underestimated. Thermal expansion, of course, is the change in ocean volume, but these are all changes in ocean mass. So, as you well know, in a glaciated area, your ice sheet history is critical, and that's part of reconstructing past sea level changes. This simply shows you that people have done really sophisticated work with satellite data on sea level rise from altimetry, and sea level is not level, as you know, due to ocean currents and ocean circulation. The combined effects of steric, thermosteric sea level changes, ocean circulation, and geophysical processes make it really complicated. And so I've noticed a trend towards more regional studies of sea level and paleo sea level. The same studies looked at decadal trends, which you can look at here. And these are critical because they're not often discussed, because most of the time you hear sea level discussed from a global sea level standpoint. But the fact is, regional differences matter. And the conclusion here is that the differences, once you take out those other factors, is attributed to ocean mass, which of course is ice. And most of us knew this years ago. But now the IPCC and others are taking it into account. That's just some background on various types of sea level studies. This was also the latest estimates of the sea level equivalent in Antarctic ice. I didn't separate out West Antarctic ice sheet, which would be about the size of Greenland, maybe a meter less. And Greenland, and then there's an inventory called the Randolph Inventory of glaciers by Tad Pepper and another group. And the IPCCs, which this is actually lower than half a meter. It's not a whole lot, but it's important because many of those glaciers are retreating and are very sensitive. There are a lot of glaciers, but they don't contribute a whole lot, which is why I kind of look at the data from these ice sheet margins and see, personally, disturbing trends. Here's one example where I know the Odin went down to the this part of West Antarctica, but the bottom line is the red is the rate of thickness change in a negative sense, so you're losing mass balance, and the blue is the opposite, and there's a lot more work going on in the margins of Antarctica. And I'll mention that this is relevant also with the big ice shelves and smaller ones to the Arctic itself and the work that the Sweareskers did, because the model has been resurrected by Martin Jakobsen and others, that these, and many German groups as well, Polyak, Nissen, others, originally by Peter Vogt, that there were big ice shelves in the Arctic. This idea goes back to an idea in the 70s. And so this is directly relevant to what happened in the Arctic since the last glacial maximum and prior glacial and deglacial periods of time. And so these are the different ways different people study sea level. I like this one, paleo shorelines. Corrected, of course, if you can, for vertical movements. The most commonly used are the benthic foram oxygen isotope records, which I'll talk about, because when you build an ice sheet, you differentially take up the light oxygen 16, and your forams in the bottom of the ocean capture that in their calcitic shells and the oxygen isotope ratio in those. I'll get that in a minute. That's been gospel to everyone, but it's got some issues because ocean temperature, the water in which you secrete your shell, affects the O18 signal as well. Glaciological data, which would be both onshore and submarine, geophysical models of glacial ice static adjustment, GIA, and what's called fingerprinting, and that's, I'll get to that in a minute. Now, I'm not a geophysicist, so correct me, all you geophysicists, if I say something wrong. It's not rocket science in a simple sense, in that if you melt Greenland ice, you get a certain regional pattern of sea level in different areas that's not the same as if you melt Antarctic ice. So what the fingerprinting efforts try to do is identify which ice sheets were melting during key periods of climate change in the past. And then last, dynamic topography due to the mantle processes, which is beyond my intellect as a stratigrapher or quaternary person on the one hand. On the other hand, it's critical for some of the periods of high sea level in the past, including the Pliocene, that I'll mention in a second. This is my favorite. Just go to Florida, drive south of Miami, drive to Key West, Key Largo. It's been known since the 60s. Some of the first uranium series dating by Wally Broker and others on corals, which is a very good dating technique. I have dated this as the Eemian, as you know it, marine isotope stage 5e, the last interglacial, when sea level was between 6 and 8 meters above present. The climate, including the orbital configuration, was roughly like our Holocene today, and the CO2 concentrations were too. Now, that raises the simple question, why was sea level higher, meaning there was less ice volume in one of the ice sheets? And that's really important for people to find out. But it's not rocket science to see a reef and to know that that reef might have lived in 3 meters of water on the top of the reef, and you put it together and you get a relative sea level. And this is a pretty stable area. There is some subsidence, but this is not Barbados or New Guinea, which are quite different. So that's the late Quaternary. If we look at the Cenozoic, 65 million years, this is an oxygen isotope curve. And people have discussed this. This is the global temperature. This is the sea level curve. Here we are in the high amplitude Pleistocene cycles, but going back to the Miocene, and then the Paleocene, Eocene thermal maximum here, and the Eocene warm period, when this is almost an ice-free world. If you want to know more about that, please talk to Jan Bachmann and colleagues about his expedition in 2004. But the point is, the glacial interglacial cycles of here are higher in amplitude and on average much colder with big northern hemisphere ice sheets. You begin to get southern hemisphere ice sheets in here, and I'm not going to talk about that much. So we know a lot about the climate history and the major steps towards the ice ages that we know from the Cenozoic record. And we also know that CO2 concentrations, which are well reconstructed here, as I showed you in an earlier slide, there's the same oxygen isotope curve from deep sea benthic forams here. And then this is the paleo CO2 using a number of methods. And I don't have to tell you that the pre-industrial is 280. The glacials are 190 to 200. And here we are in some slightly higher Pliocene levels. I'll talk about the Pliocene in a minute. Miocene. And then you go back to the Eocene warm period. and you're up to 1,000 with multiple methods suggesting that. So you're in a greenhouse world here, and relatively ice-free. We know that modern glaciers like this one, because I'm standing on a moraine, and according to Ole Ingolfsson, who led this field trip, the moraine is 19th century. So it's retreated pretty recently, as you all know, from a little ice age maximum. So we are seeing changes in sea level in many glaciers around the world where the monitoring is fairly good, and more with geological evidence, cosmogenic dating of moraines. These glaciers are retreating today, and I showed you how much they contribute to sea level. But in the past, we had the big ice sheets. This would be the, it's a little complicated, but basically these are relative sea level curves for different areas. And here's Sweden over there. Okay, and you can see the scales are all different, and all of this reflects the glacial isostatic response, not only where there were the ice sheets, but in low latitude areas as well. And here's Hudson Bay, and here we are over here, and here are big ice sheets, as reconstructed in Peltier's many papers on this topic, and the rate of sea level rise, or in the case of up here, the rate of sea level fall, number one. Number two, so we know if there's an ice sheet, it pushes down the crust in the mantle and rebounds. But outside the areas of the ice sheets are areas like where I live right here, or you have over here, and possibly in the Arctic, based on a lot of the new discoveries up there, called a peripheral bulge, and after the ice sheets retreat, a collapsing forebulge. And those are the areas where the rate of sea level rise today, due to this process, is greater than the global mean. So sea level is rising faster in the Chesapeake Bay, Washington area, and even down to Louisiana, New Orleans area, where you have tremendous subsidence. So there's subsidence going on, while where we are here, you have uplift. That's your glacial isostatic adjustment, which is actually fairly well understood based on 40 years of combined relative sea level curves and geophysical modeling. And some of you probably know an awful lot about that. Here's Boston. So all these curves are different depending on where you are. If you go to the East Coast, this is a really good example. I live about here. There's Delaware, Virginia, New York, Boston. Okay, and this is the land level change in millimeters per year. And it's varying because this is the area that was not glaciated, just outside the southern margin of Laurentide ice sheet. And that's your peripheral bulge that was pushed up when the ice sheet was there, and now it's subsiding. So your rate of sea level rise due to this glacial isostatic adjustment is high. This is really important, and usually is factored into analyses of a sea level curve anywhere you go. So that's glacial isostatic adjustment reflected along the eastern United States, and there's a big literature on that based on Holocene sea level records. There's some references up there. There's more. This is this idea of fingerprinting. Jerry Mitrovica first published a really seminal paper, 2001, I think, on the geophysics involved. Relative sea level change, as would be measured by target environment, caused by a mass loss of 1 millimeter per year, average sea level rise, assuming melting occurred uniformly. Okay, so if you look at the top, you see a certain pattern of relative sea level rise based on this gravitational rotational factor, and a very different pattern if Antarctic melted. There's actually a really nice study, Bamber, 2010, where they took all of the mass balance of modern glaciers and said, and did this analysis to try to see if it fit the model. But there are more studies on paleo sea level that try to look at fingerprinting. Take, for example, the Eemian I mentioned before, the interglacial with 8 meters of sea level rise, to try to figure out what ice melted that caused that relatively small in terms of glacial, interglacial, but really important for society, if just 1 meter would be important, during that Eemian by doing this kind of fingerprinting analysis. Likewise, for the warm period, 400,000 years ago, marine isotope stage 11. So, no, most studies don't take all these things into account. So I'm going to talk briefly about certain periods of time. I'm going to start with the Pliocene, one of my favorite periods. They changed the definition of Pliocene, it doesn't matter. We're talking about 3 million, 3.5 million years ago, okay? And that's the total Pliocene. The Pliocene warm period is what I just said, 3.5. High sea level, 20 meters. That's much higher than the Eemian. And it's pretty significant ice loss. There was elevated CO2 concentrations, but there's a large error bar. So if you want to do a nice thesis and get a job, do a better job on reconstructing CO2 with preferably organic biomarkers. Relatively warm and climate, but most important, when you hear this magic number, 2 degrees sea warming, dangerous level, what's dangerous, right? 1.5 degrees, 350.org, all of this stuff that's been influential in making people address the issue from a policy standpoint. We don't want to go there. What they're talking about, for the most part, is we don't want to go to the Pliocene, okay? And that's why a better estimate of that would be important. There are many modeling groups, at least a dozen, modeling the Pliocene climate, and there's less than there used to be proxy people doing sea surface temperature and land temperature reconstructions of the Pliocene. And Ken Miller, I got to really, okay, so this is not new. If you look here, on the deep sea oxidized isotope curve, known as the Lysacki and Ramo stack, it's a composite of deep sea isotope. Here are your high amplitude late Pleistocene interglacial glacial cycles, and here are your 41,000 year molecular cycles. These are called 100K cycles. And here's your Pliocene in here, and the lower values of 018 versus the higher values means there was less ice and or warmer temperature in the deep ocean. So these records have been around for 25 years, and now it's been more comprehensive study of this period of time, including sea level. Do I have a little neat, huh? I did that myself. So there's your mid-Pliocene that so many people, including policymakers, are focusing on. So I thought I'd throw it in because we wrote a paper on it in 1990, trying to estimate the sea level from the East Coast of the United States, which is what I'm going to revert to here. That's the eastern U.S. Florida's down here. This is Georgia and South Carolina. And you can see this geomorphic feature, which is a shoreline, and it's a Pliocene shoreline. It's called the Årets föreläsare. Many people who don't know what they're talking about, but have started to study this, call it the Årets föreläsare, all the way up almost to Washington, but it's not. It's different, Thornburg scar, but that's okay. They don't know the geology, but they know the importance, and this would be the Atlantic. And of course, our sea islands, our barrier islands are up here. But that's a paleo shoreline, so the trick is to estimate its uplift, A, and B, its age, which we have good age data on. But it's very clear-cut evidence, like that Key Largo limestone, for a high sea level. Now, Ken Miller from Rutgers did a nice recent study. I know it's ugly. But the bottom line is he studied all the Pliocene methods, including deep sea temperature that we did to try to subtract the temperature factor from the 018. Then you only have an ice volume signal. And what you see here are different elevations, and here's age, and there's that Pliocene warm period. And they came out with a conclusion that it all points to about 20, 21 meters above sea level, which implies a very unstable, probably West Antarctic ice sheet and maybe parts of the East Antarctic ice sheet. So there's a lot of information available from different methods, including shorelines, to suggest high sea level, but that's not enough. So some really smart geophysicists from Chicago, Dave Rowley and a group, did reconstructions that include this concept of dynamic topography and the glacial isostatic adjustment. Subtracting those, that's what our East Coast would look like by factoring in the geophysical data, not just the shoreline, its age, its elevation. And we were underwater a lot, which I knew from the geology on shore, but now they've done a better job of quantifying it. And they came up with the conclusion that the East Coast is not a good place to study sea level. I said, what did you go there for? You know, I don't know. Berate them. No place is a good place to study global sea level unless you factor all these things in, and the more you know, the better. Both the models, geophysical models, and the empirical data. So what they meant was these dynamical processes influence sea level, more so 3 billion years ago than we would worry about in the last couple of 100,000 years. So now I'm going to turn to glacial and interglacial climatic cycles, which many of you know well. And about 130 meters from the high interglacial to the glacial maximum, although some of the glacials probably had lower sea level, like marine isotope stage 12. But you're seeing sea level above present day despite the CO2 concentrations near pre-industrial levels. Okay, that's the point I raised before, which I think is very important and warrants attention as to whether or not, you know, what other factors other than CO2 were important, because it wasn't CO2, not directly at least. So then we turn to this very nice summary article on the 40th anniversary of the most famous paper of all in paleoclimatology, and that would be Hayes, Embry, and Shackleton's Pacemaker of the Ice Ages. Eccentricity, obliquity, precession of the Earth goes into the climate system with complicated feedbacks, which are probably responsible for those 6 meters in the state 5e. And then what comes out is the deep sea isotope curve, sea ice, glacial ice, and the interglacial. Glacial, interglacial, okay? They carefully use the word pacemaker because they're not saying the orbital changes in the solar energy hitting different latitudes and different seasons. They're saying it's a pacemaker, but that climate system, including CO2 feedbacks, are what really matter in reaching a full glacial during the last few 100,000 years. This idea, this approach, has been extended back to the Mesozoic. There are orbital cycles everywhere. At 2 o'clock today, I'll talk about some of them, which are unbelievably advanced studies of cyclic sediment sequences. But in this case, we have the advantage of also having the ice core CO2 record and a long history of study. So if we go back to the 018 curve here, let's get our labels in. There's the 100K cycles. There's us in the Holocene, the last glacial maximum, the Eemian, and I mentioned stage 11 here, and see how deep the 018 curve, how heavy it is, which would imply either greater deep sea temperature cooling or larger ice sheets, okay? So that's our context for the glacial interglacials. Well-known transitions occur here at the mid-Bruns, Bruns being the paleomagnetic epoch of the last 7,000 years or so, and the mid-Pleistocene transition, which is getting enormous attention because nobody really understands why we went from the 41,000 tilt cycles to the 100,000 cycles. There's no shortage of ideas on that. Here in the East Coast, which I like, because I work so much there, that's a geologic map put together by an old friend of mine, now retired. And I don't have to tell you, if you do real old-fashioned geological mapping, you can see the coast parallel colors reflecting the different transgressions and regressions, or at least the major ones, during the last couple of million years, younger than the Pliocene Orangeburg Scarp in here. And so these are quaternary transgressions, and of course regressions where the sea level was much lower. And the Key Largo limestone was down here, much of marine isotope stage 5. And so my student is finishing his PhD, he's defending in a month. He's been redating these with uranium series dating, and much of this is his work. And we're going to come out with a paper where we're trying to synthesize with all this new data the evidence for high sands during the Key, stage 11, and of course stage 5E, and to factor in the fingerprinting method. So this is in the works, but it shows you on a passive, quote unquote, passive continental margin, how much of a sea level record you have. So I wanted to get back to the 018 curve, which is, and by the way, never, one of the reasons in the Arctic work that's gone on, the key chronology comes from Jan Bachmann and nanofossils in the young part radiocarbon, Matto Reagan's astronomical tuning, and all your guys' stuff and other people. But it doesn't come from the oxygen isotope stratigraphy, which is used globally to correlate deep sea cores. Next week at the PAST conference, I'll talk about some new data on oxygen isotopes from the Arctic that are a really, really preliminary attempt to try to establish an 018 stratigraphy there. So if you're Arctic oriented, I can talk to you later about it. But I wanted to get to the 018 curve, and that's a benthic Cronin curve. There's a parallel curve from the Red Sea and the Mediterranean by Bert Bolin, which is almost identical, but that's a planktic Fourier curve because the Red Sea, with these sea level changes, the sill depth changes, and the hydrology changes, and it's a beautiful 018 record, completely independent of the deep sea here. And then, of course, the coral reef records, and these are the things that go into the 018 curve, and here are all the sources of error, okay? I won't go into them in detail because I've alluded to some of them, what magnitude viscosity do you use, hydroisostatic effects, and so on. So let's look at this again one more time, but this time actually showing you the sea level change of 125 meters for the last, I don't know, that's a Mac to PC, don't worry about it. That's 600,000 years. What changed here at the stage 11 to 12 deglaciation, the termination, if you go back in time, is really important. And people don't pay attention to this, but the CO2 concentrations during the last 5 warm interglacials was 280. That's pre-industrial. But it was 240 here. It's 40 parts per million volume, which one would surmise might have a serious influence through all those feedbacks, now still unknown, on the scale of your glacial interglacial cycles and temperatures up top. So the link between sea level produced from 018 and the carbon dioxide curve and temperature using other proxies is still at the heart of a lot of research going on. So here are what's that? Okay, that's your North Atlantic. Oh, that's an Arctic index we put together of ice-free and ice-covered periods, ice-free being towards the top, sea ice-free. This is modeling by Bas de Boer of the Northern Hemisphere ice shelves. That's a glaciological model. That's the relative sea level from the Red Sea. I told you it was almost identical to the Lysakian rainbow curve. And you can see that. Here's your glacial, and here's stage 5, Eenian E, C, and A. And here is Elderfield's reconstruction using DBC benthic forams corrected for temperature using an independent method. And there it is. So we have all kinds of estimates of ice volume and or sea level. And we know the patterns pretty well, so that if I go to this Eenian here, which you all know, you know here, there's the beautiful city of Santo Domingo. historically wonderful, musically wonderful. The rum is great. But more important is the coral reef here it's a relatively stable area, not out to the west towards Haiti, but here it is. And there's a beautiful reef that reflects the same high sea level, the Eemian of. So here's a stable area, like Florida, like I showed you before. It shows a nice reef. And there are other reefs if you go inland from the coast representing the older one. So there's a slight uplift here. But again, what's the elevation? I don't know, 5 meters. But if you go to a tectonically uplifted area, where some of the pioneering studies were done here in New Guinea, you see these flights of terraces, linear, 256 meters, the same reef high stand. That's uplift. And this was one of the classic sites that allowed people to tie the deep sea isotope curve. Why? Because you can actually date the reefs with uranium series dating. You don't date those deep sea 018 curves directly, but you can date them here. And of course, years ago, they discovered that these correspond to Milankovitch cycles as predicted by the orbital theory. And here's a cartoon showing you the different elevation in Barbados, another famous location of 44 meters versus that one I just showed you there in New Guinea. And you calculate the tectonic uplift rate and factor it in. I guess you're seeing by now, all along the way, the paradigm of the 018 and it as a sea level proxy has various sources of error, including age and calibration of the 018 from oxygen isotope values into sea level. If you go to the East Coast, no one can deny that those are marine fossils, Mercenaria, worm tubes, and everything else. And this is actually stage 5A. I won't explain the reason why, but it has to do with glacial isostatic adjustment in this area. And so you don't have to have coral reefs. There are actually corals in these sediments that are solitary, not reef building, but they're datable. There's one in North Carolina. This is about sea level, a little above sea level. So very stable areas. You can go all around the world to see these. If you weren't glaciated and had everything destroyed that was pre-last glacial maximum. So we want to go back to the curve and mention, to summarize, that's Rolling's curve, these key stars. And those are your interglacials that had higher than Holocene sea level. For reasons we don't know, and it would be nice to know that, but the precision of most of these methods doesn't get down quite to the 5 to 8 meter range. Okay, so I'm going to turn to the Arctic, I think, in a minute. And just to remind you, this old diagram, this is a cartoon of the glacial, aglacial. That's pre-industrial Holocene. The Arctic was a very small ocean. Bering Strait was closed. Ice shelves grounded below 1,000 meters. Talk to Martin Jakobsen, 800 to 1,000 meters. Perennial sea ice or ice shelves, minimum biological productivity, deeper halocline. And there's your pre-industrial. And mentioning that Jan's crews produced evidence for as much as 20 degrees centigrade during those hyperthermals in the greenhouse world of the Eocene. So here's the sea level curve, mainly from corals. Glacial maximum, I'm getting younger as this talk goes on, as you can see, glacial maximum, the deglaciation here. We know there were periods of extremely rapid sea level rise that drowned the corals, and those are called meltwater spikes, and sea level rise could have been as high as 50 millimeters per year, which would be 12, 15 times current rate. Problem is that the evidence for that is a lack of coral reef and a lack of dates. So it could have even been higher for short periods of time. But you also notice on the glacial maximum, the huge errors. And that's simply because if you date a coral with uranium series data, the coral might have lived at 5, 10, 15 meters water depth. So you only have a minimum elevation below sea level. Most of this comes from Barbados and New Guinea. Okay, so you're in a situation where we have large error bars, and you would logically ask the question, well, what about our glaciological ice reconstructions? Which is why the Odin and other cruises like that, expeditions that they've taken, are so important, because they're reconstructing ice and ice shelves and the margins of ice sheets in areas that have simply never been studied, like I'll talk about in a minute. Okay, so sources of error, the depth that the corals or any other organism live. Here's Peltier's most recent synthesis. You can see the glacial maximum, the ice margins at in purple here. Here's that non-glaciated area. I told you it's subsiding now. And here's your area. And in Trondheim last year, I saw tremendous new data and mapping in the 12K range. So this is not up to date, but this is the model. And yet, we don't have much stuff from over here until the Årets expedition went out there, which is why I think it was so important. And it went here, as you all know from talks I'm sure that have been given. And this is not rocket science. If you go to a continental margin and go down 120 meters, what might you find if there is no vertical movement in that area? You should find the shoreline, based on everything I just told you. 120, 125 meters down. It's not so simple because of all the geophysical processes I've told you about. Let's say you can date the stuff. We can. With Matt O'Regan, radiocarbon dating, we can date the stuff we recovered in cores at that depth. But simplistically speaking, should there be no vertical motion, then we should just find a shoreline or shallow water brackish bugs species that live at or near a shoreline, like in here today. Of course we do, but the elevation isn't necessarily 120 meters from some of the cores, which I won't get into in detail. There is a mismatch between the depths, the sea level depths of deposits in the 11 to 13,000 year range, not the glacial maximum, in that Siberian margin with the geophysical glacial-isostatic curves. Why? I would say, and I don't know if the reviewers of my paper like it, but that it has to do with ice cover. I'm going to be general, not sea ice, but ice shelves and or ice sheets, and some sort of isostatic adjustment. In fact, maybe even a peripheral bulge in that area. Now, this goes back to the 70s, and I remember these papers and doing fieldwork in other areas over here, where the glaciologists projected big ice shelves. Terry Hughes and Grosswald proposed this massive ice shelf covering the whole Arctic, and it was not considered correct by many who did the climate reconstructions of the glacial maximum. And now it seems it was more correct than it was incorrect, based on a lot of the work that the Odin and the Germans have done on the Lomonosov and the not far off Alaska, the Chukchi margin of the Mendeleev, and around the Yermak Plateau, where there's good geophysical evidence for thick ice shelves. And whether or not those ice shelves were connected to land-based ice sheets, I'm not going to speculate on. I'll let like Nielsen and modelers decide if you can build an ice shelf and an ice sheet. Because remember, this ocean was much smaller on the continental shelf, away from the major ice sheets that, of course, we had here in Scandinavia and the Laurentide and out west. So the sea level record is really closely linked to the ice reconstructions that people are making. And we don't have all the answers yet, but this is a nice diagram from Martin's work that shows that conceptual ice shelf and where it might be scraping. The question, this was proposed as a marine isotope state 6 ice shelf prior to the last interglacial. There are others who disagree with that and think it might be glacial maximum or even marine isotope stage 4, which follows the last interglacial. I'll let, I'm too old to worry about that. Other people can worry about that. Point is, nobody disputes the evidence for thick ice activity off in these regions. And to me, the people who don't work in the Arctic should pay attention to this. The modelers have, like Bas de Boer, in terms of modeling ice shelf history and ice sheet history, but the deep sea community has not yet. And so people look at the Lysakian-Ramo curve as though corrected for temperature, as though it were gospel in terms of an ice volume effect. And what they should do is be looking at the new glaciological discoveries and somehow fixing their calibrations of 018 to sea level. So, conclusions. How much should I? Yeah, I should conclude. Okay. In the Arctic, I mentioned the dates coming out on the new Soyuz expedition course as being 11 to 13,000, and what they basically show. And if you read Martin's paper on the opening of the Bering Strait, rapid flooding of the Arctic, of the upper slope onto the shelf at this time. Whether or not that matches a gap in the coral sea level record is questionable, because the coral people have a much bigger event during what you guys call your bowling Allerod over here, 14,500 years ago. Nonetheless, it's simple empirical data off on the continental margin. To explain the depth, you need some sort of ice sheets or ice shelves or some hydro-ice sea to adjust, to fit what's known as the global sea level curve, and that discrepancy right there. And there was a rapid increase of sedimentation once you flooded the continental shelves in that part of the Arctic. And we have different sources of error here, which I've alluded to along the way, and I won't go into. So I entitled this talk, geological perspectives on sea level, not to describe some eureka moment, but to point out all the complexities and a little bit of the history on how the global sea level curves have been put together for not only the deglacial, but for the earlier periods of time. And I think we still have a ways to go on this important topic. So I'll take any questions. Thank you.
All right, thank you, Tom. We have a few minutes for questions, but I'll just let you know the microphone here is for the benefit of the people who are watching via the internet. And so when you ask your question, lastly, you have to speak into the microphone.
Yeah, thank you for a nice talk. I was surprised to see your figure, which shows that ice volume during stage 5A might be higher than during the Holocene. It actually fits very nicely with the land-based evidence that we are now getting on ice over northern Europe and over the northern Canada. But it must be quite controversial, because I get quite negative reviews and negative comments if we say that ice volume during both 5C, 5A, and also during early stage 3 was significantly less than indicated by the Ramo and Lysakian curve.
What's your name?
Karen Helmens.
Okay. I feel your pain.
Yeah.
I totally agree.
Okay, that's very nice.
I totally agree, number one. Number two, the deep sea community they have a lot of things they have to work on, so it's not simple to correct for temperature. Most of the 57 curves in the Lysakian-Ramo stack, again, it's a composite, are not corrected directly for temperature at that core site, only a few, number one. Number two, if you just go back to Emiliani's original paper on the first few isotope stages, why did he name stage 3 an odd number? If he didn't, he had 1 or 2 cores from the Caribbean, so okay, give him some slack. The debate you're talking about is not new, of course. It goes way back to the 70s, when people were, 60s even, when they were first doing radiocarbon dating on coastal sites, and many people were finding 30,000, 40,000 year stage 3 high sea levels. And then they discounted it, okay, based on the early methods used in radiocarbon dating, that you couldn't do that, a little contamination here. But that's not a new debate about the stage 3. The stage 5 has another long history in terms of, if you track it, it used to be way down at 30 to 40 meters below sea level relative to today. Other estimates had it up near 15, up near present, so it wouldn't take much to get it above present. It's been dated, and if you've taken into account these geophysical processes in your regional study, then you have every right that everyone else has to do a relative or a corrected sea level curve. I mean, that's what you want to do. If you send me an email, I might be able to show you some other papers on that. But it's not new, and you got to believe the data. You got to believe the data. I'll tell you one thing though. I know people who go out and look at this stuff on the East Coast who don't have a clue what they're doing, and they get a date on some sediment, but they don't have anything marine in the sediment. I said, what good does that do you? It doesn't do me any good. You don't even know if that's fluvial or a dune or something. Stupid. I mean, show me a mollusk, a dinoflagellate or something. So the ingredients for success is good stratigraphy, geological mapping, as I alluded to, if you really can get that, or at least in your region, and then something marine, and then you're dating. You know, people get excited in the 70s, amino acid dating, OSL dating now, oh, it's God's gift to the world. Well, date something marine with it, and if you do that, then you got to deal with the fact that your OSL is from a submarine environment, and there's papers on that. So you're in a high latitude where these kinds of things are tricky. I'm lucky in the southeastern United States because we actually have corals, and it's a complicated thing in terms of their open or closed system, but they're not like mollusks that are open systems. So your dating is important, but if you have stratigraphy where you have Eemian, stage 5C, stage 5A, and even a nonconformity, I mean, you're golden.
Well, it's hard to get published. I can
Well,
tell you,
there are a lot of
nice
journals.
to talk to you.
There are a lot of journals out there.
Okay, we probably have time for another quick question. Anyone has one? Well, I'm not going to press Tom too much as he'll be back on stage in a couple hours.
That's true.
But yeah, we'd like to thank you, Tom, for
Yeah, it's
taking
not
the
the
time
same.
to give
It's
this
not the
seminar.
same talk either.